Jute fiber reinforced polymer composites, structure, properties, processing, and applications. Natural fiber reinforced polymer composites have emerged as sustainable alternatives to conventional synthetic fiber composites due to their renewability, biodegradability, and lower environmental impact. Among these, jute fiber composites have attracted considerable attention because of their favorable balance of mechanical performance, cost-effectiveness, and availability. Natural fibers such as flax, hemp, jute, kenif, rami, and banana typically possess low density, approximately 1.3 grams per centimeter cube, significantly lower than glass fibers, approximately 2.5 grams per centimeter cube, resulting in superior stiffness to weight ratios in composite structures. Jute, primarily cultivated in India, Bangladesh, and Nepal, is one of the most abundant lignocellulosic fibers, second only to cotton in global production. Traditionally used in ropes, sacks, and textiles, jute fibers are now widely employed in advanced applications, including automotive interior components, door panels, seat backs, trunk liners, geotextiles, construction materials, and furniture. This transition is driven by increasing demand for lightweight, eco-friendly materials in engineering applications. Composition and properties of jute fiber. Jute fibers are derived from plants of the genus Corchorus, predominantly Corchorus capsularis, white jute, and Corchorus olatorius, tosser jute, belonging to the Tiliaceae family. Their chemical composition is primarily lignocellulosic, consisting of cellulose, 61 to 73%, hemicellulose, 13 to 23%, lignin, 12 to 16%, minor components, pectin, waxes, and fats. The exact composition varies depending on cultivation conditions, harvesting time, and retting processes, water, dew, or enzymatic retting. These variations significantly influence the mechanical properties of the fibers. Mechanically, jute fibers exhibit moderate tensile strength and stiffness, governed by parameters such as microfibrillar angle, typically approximately 8 degree, fiber diameter, and degree of crystallinity. Their relatively high cellulose content contributes to strength and stiffness, while lignin imparts rigidity and resistance to microbial degradation. Morphology and microstructure of jute fibers. The morphology of jute fibers plays a crucial role in determining composite performance. Scanning electron microscopy, SEM, reveals that jute fibers possess irregular cross-sectional geometry, variations in diameter along the fiber length, rough surface texture with micropores. Such surface roughness can enhance mechanical interlocking with polymer matrices but also contributes to moisture absorption. X-ray diffraction, XRD, analysis indicates a high degree of crystallinity, approximately 92%, associated with the cellulose 002 crystallographic plane. This high crystallinity is beneficial for mechanical strength and thermal stability. Fourier transform infrared spectroscopy, FTIR, confirms the presence of hydroxyl groups and other functional groups characteristic of cellulose and hemicellulose, which are responsible for the hydrophilic nature of the fibers. Thermal properties of jute fibers. The thermal stability of jute fibers is a critical factor in composite processing. Thermal analysis using thermogravimetric analysis, TGA, and differential scanning calorimetry, DSC, shows multi-stage degradation, moisture evaporation, up to around 100 degrees Celsius, hemicellulose decomposition, around 290 degrees Celsius, cellulose decomposition, around 332 degrees Celsius, lignin degradation, around 447 degrees Celsius. For practical processing, jute fibers retain structural integrity below 170 degrees Celsius. Consequently, most composite manufacturing processes are conducted below 200 degrees Celsius to prevent degradation. This limitation restricts the choice of compatible polymer matrices, particularly high-temperature thermoplastics. Surface modification of jute fibers. A major challenge in jute composites is the poor interfacial adhesion between hydrophilic fibers and hydrophobic polymer matrices. Surface treatments are therefore essential to enhance compatibility and mechanical performance. Chemical treatments. Alkali treatment, using sodium hydroxide, potassium hydroxide, or lithium hydroxide, is the most widely used method. It removes hemicellulose, lignin, waxes, and surface impurities, resulting in increased surface roughness, reduced fiber diameter, up to 8%, improved tensile strength, up to 44%, Enhanced fiber matrix adhesion. Silane coupling agents and maleic anhydride grafted polymers, for example, MAP in polypropylene systems, further improve chemical bonding at the interface. Physical treatments. Physical modification techniques include plasma treatment, steam exposure, and gamma radiation. These methods alter surface energy and introduce reactive sites without significantly affecting bulk properties. Functional treatments. Functional treatments impart additional properties such as rot resistance, improved antibacterial activity against species like Acinetobacter, Bacillus cereus, and Pseudomonas. Fire retardancy, reduced burning rate and improved thermal resistance. Water resistance, lower moisture absorption and improved dimensional stability. Thermal analysis indicates that treated fibers exhibit lower heat absorption than untreated fibers, with fire retardant treatments showing the best performance. Jute fiber as reinforcement in composites. Jute fibers can be incorporated into polymer matrices in various forms. Particulates, macro, micro, nano, short fibers, less than 5 mm, long fibers, greater than 5 mm, woven fabrics, plain, twill, satin, non-woven mats. The form and orientation of the fiber significantly influence composite properties. Generally, the composite strength lies between that of the matrix and the fiber. In thermoplastic matrices, bonding is primarily governed by van der Waals forces unless coupling agents are used. In thermosets, cross-link networks dominate matrix properties, but interfacial bonding with fibers remains limited without modification. Processing techniques. A variety of manufacturing processes are employed for jute composites, selected based on material type, product requirements, and economic considerations. Compression molding, injection molding, resin transfer molding, RTM, extrusion, pultrusion, hand layup and spray layup. Compression molding is widely used for thermoplastics, while hand layup is common for thermoset composites due to its simplicity and low cost. Jute-based composite systems. Thermoset composites. Jute-reinforced thermoset composites, particularly epoxy and polyester systems, have been extensively studied. Fabrication methods include hand layup, filament winding, and compression molding. Studies have demonstrated that alkali and silane treatments improve tensile, flexural, and interlaminar shear properties. Surface treatments enhance wettability and fiber matrix adhesion. Jute polyester composites exhibit superior mechanical properties compared to wood-based materials. Modified jute fabrics, for instance, fluorocarbon-treated, yield significant performance improvements. These composites are suitable for structural and semi-structural applications, including automotive interiors and lightweight panels. Thermoplastic composites. Polypropylene, PP, is the most commonly used thermoplastic matrix for jute composites due to its low cost, recyclability, and favorable processing temperature. Key strategies to improve performance include use of maleic anhydride grafted PP, MAP, as a compatibilizer, surface modification of fibers, optimization of fiber loading and dispersion. Such composites are widely used in the automotive and consumer goods industries. Bio-based composites. Fully biodegradable composites are achieved by combining jute fibers with bio-based polymers such as polylactic acid, PLA. Processing methods include film stacking and injection molding. Representative studies show that jute PLA composites exhibit moderate tensile and impact properties but tend to fracture in a brittle manner. Alkali treatment improves interfacial bonding and mechanical performance. Optimized processing conditions, for example, 12% sodium hydroxide treatment, 8-hour immersion, 210 degrees Celsius processing, enhance composite properties. Other bio-based matrices include biodegradable polyesters, such as biopol, soy-based resins, and bio-epoxy systems. Hybrid jute composites. Hybrid composites combine jute with other fibers to improve performance and overcome inherent limitations. Natural fiber hybrids. Combinations with fibers such as sisal or other cellulose-based fibers improve mechanical properties and sustainability while maintaining biodegradability. Natural synthetic hybrids. Hybridization with glass fibers significantly enhances strength, stiffness, and moisture resistance. For example, jute glass fiber polyester composites show improved tensile, flexural, and interlaminar shear strength. Optimized stacking sequences influence overall performance. Hybrid systems reduce reliance on synthetic fibers while maintaining high performance. Such materials are particularly attractive for automotive and aerospace interior applications. Challenges and future prospects. Despite their advantages, jute fiber composites face several challenges. high moisture absorption due to the hydrophilic nature, limited thermal stability, variability in fiber properties, poor compatibility with non-polar polymer matrices. Advances in surface treatment, hybridization, and processing technologies are addressing these limitations. In particular, nanotechnology offers promising opportunities. Cellulose nanofibers derived from jute exhibit exceptional mechanical properties and a large surface area, making them attractive for high-performance composites. However, challenges related to extraction, dispersion, and scalability remain. In conclusion, jute fiber reinforced composites represent a promising class of sustainable materials with applications across the automotive, construction, packaging, and consumer industries. Their low density, renewability, and cost-effectiveness make them attractive alternatives to synthetic fiber composites. Surface modification techniques, particularly alkali and coupling agent treatments, play a critical role in enhancing interfacial adhesion and mechanical performance. The use of compatibilizers, such as maleic anhydride grafted polymers, significantly improves bonding in thermoplastic systems. Bio-based matrices further extend the sustainability of these composites, while hybridization strategies enable performance optimization. Future developments in nanocellulose extraction and advanced processing are expected to unlock the full potential of jute-based composites, paving the way for their broader adoption in high-performance and environmentally sustainable applications.